So today we're going to be performing the first derivative test. And now what the first derivative test is going to give us is it's going to tell us what the graph is doing as far as its motion. Is it going up? Is it going down? Or is it doing something kind of in the middle if we have a flat spot? The first thing that we're going to do is we're going to take the original function and find some critical values using the derivative, hence the first derivative test. We're going to see what happens around those values, what's happening to the left of the critical values and what's happening to the right of the critical values. And this will give us a good idea of what the graph will look like. So we can see that if we find a critical value and the derivative on the left is a negative number and the derivative on the right is a positive number, we know that is a minimum value because the only way the graph can go down and up is to hit a minimum. Likewise, the reverse is if the critical value has a positive on the left in the derivative and a negative on the right, the graph must be going up to down, therefore we get a max. Sometimes though, when we get a critical value, we'll get positives on both sides or negative on both sides. What that means is that we have a neither. This is, I guess you'd call it a point of inflection. This is one of those points where the graph is attempting to start to go back down, but then it curves right back up. These we'll see in like powers higher than 2, so if we have a cubic or a quartic or a quintic or something like that, one of those functions. So let's go ahead and use some of this information and jump right into it. So our directions on this one, number 1, we're going to find the critical values of f, then label the open intervals where the graph is increasing or decreasing, and use results to label the nature of these critical values. So we're going to find the points, state whether the graph is moving up or down, and then we're going to say, hey, this point is a max, this point is a min, and so on and so forth. So our first goal right here is going to be what is the derivative? So I know f prime of x is going to be 12x squared plus 24x minus 36. So I've got that. I want to set this equal to 0. And I'm going to work this out. So I notice that all three of these are divisible by 12. So plus 2x minus 3. We'll call that a 3. I'm going to factor this out. I don't need to use the quadratic formula. I can factor this by hand. This is going to be x plus 3, x minus 1. So my two critical values are at x equals negative 3 and x equals positive 1. Critical values. Awesome. So I know that on the graph, let's go ahead and sketch this out. So my critical values right here are going to be at negative 3 and at positive 1. And I want to sketch what the graph looks like. Is it going up, then down, then up? Is it going down, then up, then down? Is it bending right here? What's happening? So the only way we can figure that out is if we take this and we plug in some values around these points, which means I need to plug in, first off, a value in the derivative to the left of negative 3. So let's plug in a negative 4, something in the middle, how about a 0, and then something on the right of my 1, so how about a 2? And we're going to see what the derivative is doing at these 3 points. So we'll see what's here, here, and here. So let's go ahead and we could do these by hand. It's going to be a little faster if we bust out our TI-84. Can I squeeze the whole thing in? Nope. Zoom out a little farther. There we go. So let's go ahead, get our y values, and we're going to plug in the derivative. Now I could plug this in, and that would give us the graph, and we don't need to find this, but we're just going to speed things along using this. This should be something that is able to be done by hand. So I'm going to plug in, let's see, 12x squared plus 24x minus 36. So that is my derivative. Now what I'm going to do is I'm going to come over here and plug in my values. So at negative 4, at 0, and at 2. So at negative 4, I am at a 70, a negative 26, and a 70. Now, we don't really care what these numbers are specifically. What we're using this test for is I see I have a positive, a negative, and a positive, which means the graph is going up, then down, then up again. So let's go ahead and use that to graph what's going on here. So if I'm going up then down, I have a maximum point right here. And if I'm going down then up, I change directions right there. So the graph should look something like this. Maybe not exactly like that. It might be up, it might be down. Weird things might be happening, but I have a maximum point here and I have a minimum point here. So max and min. So there we go. We have our critical values. We plugged in points around them and we saw what the function was doing. So what we could theoretically do is we could then plug this into our calculator if we want to check our work. And again, realize we used a calculator here to speed things along, but this theoretically can all be done by hand. We don't need to use a calculator. Let's pop over here. I'm actually going to clear this out. Let's take a peek. So how close were we? 4x to the power of 3 plus 12x squared minus 36. Nope, 36x. So I should see a function that goes up, then down, then up. So up, then down, yep. Now, as we see, it's a little more exaggerated than that, but we have a function that goes up, then down, then up. At these points, I should have a maximum and a minimum. Now, I'd have to zoom out quite a bit. So let's set the window. How about y equals negative 50 and 50? Still not quite in there, but I noticed that at that value of 1, boom, we have our minimum point, and at 1, 2, 3, that looks like that is exactly where our maximum point is. So, good job. So now let's take a look at the next one. So you've seen it once. Give this a shot and see if you can't sketch the curve using only the values in the derivative. Pause the video and pause it when you're done and see how well you did. Okay, so now that you've had a shot, let's give this a try. So this looks like a u-v function, so we can do a product rule. If my u is 3 minus x, u prime is negative 1. If my v is e to the x minus 3, my v prime is going to be, okay, let's come do a routine. Let's do the routine in blue. So I know that if u is x minus 3, u prime is 1, f of u is e to the u, f prime of u is e to the u again, which means that I'm going to get this, yep, so this is e to the x minus 3, so we get that. Perfect. So I'm going to product these things. So I get a negative 1 times e to the x minus 3 plus 3 minus x e to the x minus 3. And this is my derivative. So I'm going to label this as, squeeze it over into the other one, f prime of x. Now, using this derivative, I'm going to find when this is equal to 0. Our first thing we notice is that I have 2e to the power of x's going on here. So again, these are designed to be done by hand. I can use the calculator to speed things along, but I could conceivably do this by hand. So e to the x minus 3. Factor out, I have a negative 1 plus 3 minus x. Boom. I'm setting this all equal to 0, which allows me to solve two different parts. E to the x minus 3 is equal to 0. And then this is going to simplify down into 2 minus x is equal to 0. This one's not hard. Critical value at 2. I want to see what type of value that is. This one is an interesting point because no matter what value I plug in, I cannot get e to any power to be 0. But it does tell us something about the behavior of the graph, and we'll come back to this here in just a moment. So let's go ahead and put a pause on that. So let's do the graph right here. So I already know that I have a value at 2 that I'm wanting to check out. So I have to plug in a value on both sides of 2. So let's section this off. So let's plug in the value to the left of 2. So let's say f prime of 0, and the value to the right of 2, f prime of 3. Okay. So again, I could plug this in by hand. If I said 0 minus 3, I could figure this out. We're going to, again, hustle things along a little bit just to see what's going on so we get this point across. Let's go ahead and clear all this, go to our table, delete some values, and reset the zoom. So I'm plugging in my derivative. So e to the power of x minus 3, and then 2 minus x. I went ahead and I simplified this as I plugged it in, because this is still the derivative even though we've set it to 0 by here. But we've got these. Let's go to our table. I'm going to plug in a 0 and a 3. Now when I plug in 0, I have 0.09, and here I have -1. Again, I don't really care what the values are. I see a positive number and a negative number, which means the graph is going up and then down. So the only way that the graph goes up and then down is if I have a maximum point. So this point is a max. Now, here's the idea, is that this maximum point, we're going to see a different type. This isn't going to form just like a quadratic or some version of that. This is going to come back into play because we know this wants to be a critical value. And so let's think about what type of number could I plug into this exponent to get it to be 0. Well, if I plugged in really, really, really big numbers, let's say 10, 100, 1,000,000, I'd get a bigger number. So I'm not approaching 0. If I plug in smaller numbers or negative numbers, that means we flip this and it's 1 over that. So if I plug in like -100 or -1,000,000, I'm saying 1 divided by e to the million. That's really, really, really close to 0. So what we're looking at is that we actually say if we can plug in x equals -infinity, we'll have another critical value way over here. And so what's going on at -infinity? Well, the graph was going up, but at -infinity, it's going to curve down. Doesn't really make a whole lot of sense, but it does mean that at -infinity, we have an asymptote. The graph is curving up at every point after -infinity. It'll never reach there so that at the edge, it can't curve down. Or it can't curve back up, I should say. It doesn't curve down because it's on the other side. However, over here, it's just going to straight dive because there's no positive infinity over there. So this would be a minimum. Or realistically, this is an asymptote. Cool. So let's double check and see if that is the kind of graph that we get. So let's come back to our y equals. I'm going to go ahead and clear out the derivative because, again, this was just to speed things along by hand. Let's see what that graph looks like. 3 minus x, and then e to the power of x minus 3. Let's zoom standard this. Okay, so I do see the fact that we have the plunge, right? But I don't really see what's going on right here. So let's zoom in. Looks like we can get away with maybe a -1-to-1. Okay. So we do see that it plunges up and then plunges down. But again, I want to see a little closer to what's happening here. So let's try -0.1 to, actually we don't even need, oh yeah, let's do 0.1 to 0.1. Shloop. So it does look like the graph is curving down just like that. So good job. So now this brings us to extension of that same idea to this back half. We're going to find all critical values of the function along the interval from 0 to 2 pi. We're going to use our TI-84 to graph the first derivative. And looking at the graph, we're going to label those points as either maximums, minimums, or neither. So as the extension, this would be more the calculator version or the technology version, where we can go ahead and plug this stuff in and just look at how the graph is doing to sketch the curve. So let's take a look at it. The first thing I need to do is find the derivative. So f prime of x is equal to 1 minus 2 cos of x. I know that derivative, I'm going to set that equal to 0. So negative 2 cos of x is negative 1. Cos of x is 1/2. Okay? So the cosine we know is adjacent over hypotenuse, or the x value over the r value. So on my unit circle, what I'm looking at is x over 2 is a positive 1/2, which means that I'm having to look at the right half of the graph. So wherever I draw this, cool, the adjacent is going to be 1, and my hypotenuse is 2, which if I look at that a little closer, that's a 1, 2, square root of 3 triangle. That's a 30, 60, 90. So 30, 60. So that's 60 degrees. And if we're looking at 2 pi, 60 degrees as a 2 pi is pi over 3. And I have a negative 60. So let's figure out. So 2 pi minus pi over 3 is going to give us our other value. So that will be, let's see, 6/3. So 5/3 pi. My two critical values that I want to find out, what type of value are those, simply looking at the graph of the derivative. So we're going to sketch this. Clear this, and let's go back to a standard zoom. So 1 minus 2 cosine of x. Oh, yeah. And so before we continue that, let's set our window from 0 to 2 pi. And because I'm dealing with increments of 60 degrees, I'm even going to set this as increments of 60 degrees. So pi divided by 3. So I see a critical value at my first pi over 3, 2, 3, 4, and at 5 pi over 3. Okay. So I'm going to translate this onto this graph. And because this is the derivative, let's set this in blue. There we go. So this is my f prime of x. So I see that at pi over 3 and at 5 pi over 3, I have values. So what is the graph doing? Well, when the derivative is negative, the graph is going down. When the derivative is positive, the graph is moving up. And then when the derivative is negative again, the graph is moving down. So I know my graph is going down and then up, and the only way it can do that is if it changes directions right there. Up and then down, the only way it can do that is if it changes directions right here. So I'm going to go ahead and connect those points. So now this may not be exactly what it looks like because I kind of went straight right there. But this should be the original f of x. So this is going to be a minimum, and this is going to be a maximum. And so let's test out and see how close were we to this graph. And let's plug in the original. Clear that. So x minus 2 sine of x. We have a minimum point right there and a maximum point right there. Got to scale off a little bit, but you know what? That's the overall shape of the graph. So good job. So why don't you go ahead and try number 7 on your own. Go ahead and pause the video and pause it when you're done and see how well you did. Okay, so let's try this one out. Number 7. I'm going to find the derivative. I'm going to use the derivative of the graph to sketch what the higher order function is going to look like. So the first thing I do is I see a product rule. So u is the sine of x, which which means u prime is the cos. And if v is the cos of x, then v prime is the negative sine of x. I'm going to use this information to pop these two. So I have cos squared x minus sine squared x. And this is my f prime of x. Let's zoom in just a little bit. That might be hard to read. So after I did my product rule, 5 disappears. I get this, and I'm going to set this equal to 0. Now, this looks dangerously close to the Pythagorean identity, but can't really do too much here, other than what I can do is I can add the sine squared x to the other side. So when is the cos squared x equal to the sine squared x? Let's break it down a little further. What does the cosine stand for? Cosine is adjacent over hypotenuse, so x over r. The sine is the opposite over the hypotenuse, which is the y over the r. I notice that because they're both squared, I can take them down. It doesn't matter if they were negative or positive at this point, so I could have both positive or negative of either one of these. And what I'm really looking at is when does the x equal the y, both positive or negative, on the unit circle. So if I take the unit circle and I look at it, when does the x equal the y? Well, let's do this in purple. The x equals the y at every increment of 45 degrees along here. Not at the 90 degrees, but at every, not sure how we describe that, but at 45, at 135, at, let's see, 225, and at 315, which would be my values. X equals pi over 4, so 1, 2, 3 pi over 4, 3, 4, 5, 5 pi over 4, and 7 pi over 4. So I'm looking at those 4 values. So let's go ahead and we're going to plop this into our graphing calculator, and we're going to sketch the curve. So let's clear this and reset our zoom. So we have cos of x squared minus sine of x squared. Remember, with the calculator, I can have the square over here, and that's equivalent to when we write it with the squared in there. And I'm going to set it from 0 to 2 pi. And because I'm dealing with increments of 45 degrees, I'm going to do that in increments of 45 degrees, so pi over 4. And while this is graphing, what we know is that we have 1, 2, 3, 4. Each increment right here. I know that, let's see, we did the original one in blue. So let's say the graph goes up, down, and up. So what I know is that the graph is going up, then down, then up, and then down every time it crosses over and up. So if the graph went from up to down, I have a max. Down to up, I have a min. And I have a max. And it goes down to up, so a minimum point. So my graph should look something like this. And so let's see if we get this shape if we actually graph the parent function. First off, I know this plus 5. This is probably going to be way up here, but regardless. Let's see, sine of x, cos of x, plus 5. Yep. So because that's a little blurry, what we're going to do is, let's zoom in just a little bit. Let's say +5, so we're going to deal with, how about 3 to 8? Goes up, down, and up. Perfect. We got it. So there you go.